let me share my screen and then we can start ahead. Okay, so today's topic is on AI with TensorFlow. So before we start, just a brief introduction of myself. I am currently working as head of AI at Redbuffer. Redbuffer is basically an AI-based services company. So we work out of Pakistan, but we give services to companies in Europe, USA, America, Australia, all over the globe, and in Pakistan as well. I am also a tech blogger on Medium, and I'm a Google developer expert in machine learning. So before we dive into what TensorFlow brings to the table, I think it's important to understand, what we really have out there and how AI has progressed over the years. So AI actually dates back to 1943 when the first mathematical model of a biological neuron was built. Now, AI, we have heard this many times that it's inspired by how the human brain works. And how the human neuron basically works is that you have dendrites, which basically take information from a previous neuron. Then you have soma, which basically processes that information. Then the axon and the synapses basically give the output and connection to the other neurons ahead in the path. Following this in 1950, the first paper was published that basically questioned whether machines could think or not. And this is where the Turing test was also introduced. So the Turing test basically is a test for computer intelligence, where the computer intelligence is tested by whether or not a human can differentiate between a computer and another human being. So, for example, if is person C, when person C is communicating, whether they are able to differentiate between how A is communicating with them and how B is communicating with them. So, whether or not C is able to differentiate between the computer and the human. So, this is what's referred to as the Turing test. Then in 1958, basically the biological neuron, even though initially introduced, but this is when the first, you could say that the supervised algorithm was built. So this was the first modern neural network, the first perceptron where in research, they were taking into account the different weights and trying to get an output for that. And then basically Hinton came in and he started to work around a lot of ideas relating to whether or not computers can think like humans. And this is one of his famous quotes where he says that, the brain has got to do work somehow, and it sure doesn't do it by writing programs and sticking them. So human beings are not programmed. Human beings have some common sense. So whether or not that's something that can be replicated in computers. So after about 30 years of his efforts, where a lot of scientists thought that what he's saying is it then doesn't hold much value, after 30 years of that, starting from 1986 to basically 2012 is when a lot of his theories were considered accurate. But when we talk about, so even the chatbot is a very recent hype in machine learning, so natural language processing and chatbots, that's a very recent hype, and there's a lot of research that's going on into how advanced chatbots can be. But 1966 is actually the time when the first chatbot was built, or as we would like to call it. And this was a research that was done by MIT back at that time. So even though it was just a, like a text input output kind of a thing, but this was still what formed the basis for a lot of research that was done eventually. And then we saw a lot of advancements that came in. So in 2016, we saw that AlphaGo, that a computer program was able to defeat AlphaGo champions. Then in 2017, Stanford released an algorithm that diagnosed about 14 different medical diseases, and it could diagnose pneumonia better than the radiologists. Then in 2018, we got the first self-driving cars in. Then we had the open AI bots that defeated the Dota 2 champions. Then in 2018, Google's duplex AI basically passed the Turing test. So if we recall, Turing test is where a human being, is unable to differentiate between another human being and a computer. In 2018, Google claimed to have passed the Turing test. So now coming into some of the recent things that have been happening in artificial intelligence and some examples of the kind of power that AI brings to a lot of our problems. So one of them is, for example, if we look at language independent segmentation of different areas based on vision. This look like? So you have a lot of different PDFs, you have a lot of different pages, you have them labeled into different segments. And if this is something that you normally have to do, for example, if you want to extract some important information, then manually you would have someone go through that PDF. If it's a 10-page PDF, a person would manually take about like 7 to 8 minutes. But when we compare that to AI, what that process looks like is that you scan a document, the AI helps to segment it into logical sections, and then the NLP is used to extract the information from those different segments. And all of this process basically brings down that manual labor from 7 to 8 PDFs to about 30-40 seconds. So even if to improve the accuracy, you still do a manual by another human being, it'll just take at tops 1 minute. But what you're getting in speed is that in comparison to a single PDF, 15 PDFs through AI in that same amount of time. Similarly, if we talk about the other powers that AI brings into the different problems we have. For example, we want to install solar panels on rooftops. And normally what happens is that you have a team of people that comes in, they look at your rooftop, they analyze it, they look at the different things, like for example, the direction of the sun, the trees, the surrounding areas, and then they come up with a plan of what are the best areas on your rooftop, the best regions where you can have the solar panel installed. Now, all of this system can be automated through AI, where basically you give the images to your AI model, and the AI model helps to first segment the different areas of that rooftop, and then eventually takes into account all the different factors, for example, the trees, the sun direction, etc., the shape of the roof, and comes up with the best possible plan that according to it for the solar panel installation. Now, what we are doing here is that if you want to install solar panels in houses on an entire zip code, I know that's something that would seem impossible, right? For a team to go to every single house, basically, it would take way too long, right? Way too long. And this seems like an impossible problem for to be done in a given amount of time by human beings. But AI can solve these impossible problems, and that's because it can achieve the speeds that humans that's not humanly possible. So, for example, if we look back to the PDF review, so if we look at how many documents AI can review in a day, that'll be about like around 3,000. So now that's something that's not possible for a person to do manually, right? So AI can solve impossible problems, and it can achieve speeds that are not humanly possible. So a lot of times we tend to think that AI is way too smart than human beings, but actually what makes that smartness is actually the speed that AI brings in that makes it look so smart, so smarter than human beings. So now coming to solving all of these problems, and that's where TensorFlow comes in. So TensorFlow is a very powerful machine learning framework, and that's basically its unique selling point. Now TensorFlow by Google, it has a lot of other functionalities that are designed to make your life easier as a TensorFlow developer or as a machine learning developer. So you have TensorBoard, you have TensorFlow Lite. We'll come to those. TensorFlow is used for both production scalability. It's well documented. It's used in research as well as production. It gives you the ability to run parallel executions across multiple GPUs. They now also have TPUs. It gives speed that's good for high performance. It has a community that's super active, and you have different things coming into TensorFlow every now and then. So companies that are already using TensorFlow Lite are, and Google uses it a lot in its own products. So in a lot of cases, you would see that Google continuously embeds models from TensorFlow and TensorFlow Lite in its own products. So for example, the text predictions that come into Gmail when we are writing emails, that's one of Google's models as well. And then we have Google Rank Brain. So this is the model that Google uses for ranking the different links whenever we search something on Google. So whenever we search something on Google, the Google Rank Brain is the model that runs to bring the best suited links back to us. So we also have cloud TPUs. So these can be programmed via TensorFlow as well. Overall, this is the picture of TensorFlow. So you have all of these different modules for TensorFlow. You have TF data, which is TF data sets for your data processing and for your data pipelines, basically. Then you have Keras, which is the API that you can use for model designs. You have it's applicable with both CPUs, GPUs, TPUs. You have all of these. You have TensorBoard for the analysis of your machine learning models. You have the TensorFlow Hub, where you already have a lot of model repositories, reusable models that you can use just by picking those up from the model repository. You have TensorFlow JS, TensorFlow Lite, and TensorFlow Serving, which is also in high demand now. So starting off with Keras, so this is the API that we use for model building. Now TensorFlow has broken down their framework into a lot of different stages as well. So for new users, and they just want to build simple models, you can use the sequential API and you can use the built-in layers. And then engineers who want to use it for standard cases for building products, they can use the functional API and the built-in layers. Then engineers who want to write their own, for example, their own cost functions, they want to write their own evaluation criteria that they want to evaluate their models on. For example, they want to have a different method for how they define accuracy of that model, so they can write their own custom losses, custom metrics, or custom layers. And then we also have something for the researchers, where basically they can write everything from scratch in TensorFlow, from classes to the loss functions, the layers, and everything else. So now coming to look into how we can, for example, solve one of the problems. So this is a sample problem for cache recognition. So if we are trying to recognize two different types of cache, so this is the 10 rupees node and the 100 rupees nodes from Pakistan. So these are some samples from the kind of data set that's being used for this. So and so how would we train the model around this? So TensorFlow has some Keras has some very good model we can use that also now helps with how we ingest the data into the models. So one of the first things that we can do is that we can have a folder structure similar to the one that you can see on the screen. So you have images, you have a training folder, a testing folder, then you break it into further classes. So 10 and 100, we have two classes, so we have two folders, and each of these folders basically has the images for that class, right? So we have images, then we have training and testing. So for training, we'll be using the training main folder, which will have two subfolders for the two classes. If you have more classes, so you'll basically have more subfolders here. And then the corresponding and respective images would be in those folders. So what's the best way of solving this problem, right? The data that transformed the AI research. that's the data with 3.2 million images, about 12 subtrees. This is the ImageNet data. So one way of solving this problem is to basically use a pre-trained model and then fine tune it on our own data set of the cash rupees. So how the structure basically look like is that we would have a pre-trained model that we're using. We already have seen what our images directory looks like. So that's the one here. So this is our images directory. Then we'll basically be using one of the functions, the image generator function in Keras. So we'll be using that to load images from the images directory. So what image generator basically does is that it recognizes the different classes through the folder names, right? So it will automatically recognize that you have two classes because you have two subfolders, 10 and 100, and then it would associate everything that is in those folders to that class, right? And you while you are so it loads the images on the run, right? And if you want to augment, and it's very good to use when you want to augment on the run, right? So one of the ways that initially previously what we would do is that we would take the images, we would do augmentation ourselves, zooming in, rotating, cropping, etc., etc. And you would have these different sets of different types of augmentations, and you'll be when you want to test on the different kinds of augmentations and see which augmentations perform well, you'll basically be loading the three different types of data sets, and then preparing the three different types of data set, then loading them, and then training and testing. What image generator does is that you can do augmentation on the run. So you can define whether or not you want zoom, whether and of what scale, whether you want to crop the images, whether you want to rescale the images, whether you want to add any shear factor, whether you want to have rotation. So there are a couple of things that common augmentation things that you can do using image generator and on the run. So you don't have to prepare basically the different kinds of data set. So that data will then be fed into the model. So we're getting the pre-trained model, any model that you can you can use different kinds of model, but in this case, let's assume that we're using MobileNet. So we're using a pre-trained MobileNet that's trained on ImageNet data already. So what you would do is that to fine tune this model to your own data, you would add some additional dense layers, you would do the training, and then you would do the evaluation for that. So what we do is we plot the different kinds of graphs that we want to see: training, validation accuracy, the confusion metrics, etc. And we write these codes in our Colabs or notebooks. Now, one interesting thing that TensorFlow has is the tensor board. So you can just use few lines of code to integrate tensor board. And what tensor board does is that it gives you all of this information and insight into your training right from its dashboard. So you can see while your model is training, you can see how the loss is dropping, how what's the validation accuracy. You can also see some sample images. You can see the different kinds of graphs and a lot of other information that you can get from this tensor board. And the integration is just a few lines of code. And now one interesting thing and something that's been creating a hype in the past year and a half is the TensorFlow Lite, where a lot of people are now working to basically make models that they can use in mobile apps. They can models that they can use for inference on iOS and Android. And a lot of work is being done around this now. So TensorFlow Lite is what you can use from the TensorFlow framework. So this helps to run machine learning models on mobile or any embedded devices, basically. Machine learning inference with low latency, and small binary size. And so basically the TensorFlow Lite converter helps to optimize the size of that model for the mobile and to carry out inference on the mobile. So this is how the basic breakdown looks like. So you train a model in TensorFlow the way you normally do, and then you basically have a TensorFlow Lite converter. You use that to create your .tf Lite model file, and that's something that you load into your Android app or your iOS app, and then you can use it for interpretation on your mobile apps. So we can also use TensorFlow Lite. It's not just limited to mobiles. You can also use it for microcontrollers. So you can use it on Arduino. We look into one sample example of what it does. So what they're doing here basically is that they're taking some sensory data from the Arduino, which is the motion data. They've built a TensorFlow model that takes that sensor data and basically classifies the gesture that's being made, and then they're running this on their Arduino. Similarly, we also have TensorFlow JS, which is for the web browsers. So one interesting application that was built for TensorFlow as a TensorFlow JS example was POSNet. So what this does is POSNet is a machine learning model that helps to detect the poses of a person. So for example, so in short, the stick figures basically. So you can see that in this video, it's continuously for each frame, it's detecting the pose of that person. So how this basically works is that you have a mobile net that's on a high level. This is basically a convolution neural networks that's being used to get the key point heat map and the offset vectors, and both of those things are being combined to basically get the pose estimation. An interesting application that was built using this is basically this. It was called the Move Mirror. Uh, So what basically they have done here is that they take your image, whatever you're doing in that image, and then they try to match it with a database of 80,000 images. So they try to match your pose with an image from those 80,000 images, whichever matches most to your pose. And as you're moving and as your pose is changing, so basically the image is changing, and that's what produces the dancing images. So the image change, that's how that comes in. Now, since I've mentioned TF Lite and also have a follow-up Kotlin, so I'm just going to run you through some of the things, how this works. So this is basically is a cache recognition projects. The one that the one that I showed was inspired by this repository by Kshitij. He's a GDE from Nepal. So how this is initially working is that you're importing all of these different packages. You have some custom defined functions just for printing the images. And then what you're doing is you're defining your session. Since this was made a while back, so now we have Keras and integrated directly into the TensorFlow framework. So a lot of these things have become less complex, basically. So you're defining the batch, the epochs, the image size, etc. You're taking a pre-model, one that's trained at and then you're defining, here is where you're defining your image generator. So you can see that we can have the rescale, we can have rotation ranges. So we can define all of these things. And when we basically load our images, so all of these things will basically apply to all the images from that directory. Similarly, you define a train generator, and then you can also define a test generator. So when you're testing, it will perform the same scaling factors and then pass them to the inference. So these are some of the images from the data set. So you add, you use the pre-trained model and you attach some additional layers to it. And then basically your last layer of the number of classes that you have. This is a summary of how the model looks like. You compile the model, you fit it. Once it's fitted, you can evaluate it on your validation data set. This is how the training accuracy and validation losses look like. You can save the model. So this is where we were saving the model as we normally save the model, right? So this is the .h file. Now we can use the same to basically convert our model to a TF-Lite. So this is a simple savings, and let me just find where it's being saved to convert it to TF-Lite. Okay, so this is basically the command, just one liner that you're using to convert your model to this cache.tflite5, which you can then use in your Android or iOS apps. Um, Google has also given this very good convert TF object detection API model notebook in their Colab, and they give a complete walkthrough of how you can do this. So in this as well, what they have done is they've just imported some TF-Lite support libraries. Then they are installing the TensorFlow object detection API, the necessary libraries. So they are basically taking a pre-trained model. So from the TensorFlow model repository, they're just downloading one of the pre-trained models, and then they're saving that. They're basically fetching the graph of that model first, and the second step that they do is they convert it to TF-Lite. So this is basically just a few lines of code. These three are the main lines basically that are being used to convert the model to TF-Lite. And once you have that, you can also add metadata. So what metadata is, that metadata has two main things. So one of the main things is the label map. So that is what defines the number of classes and basically a mapping of those classes, right? So if you have about 10 classes, so you would basically have the mapping for those 10 classes. So 0, 1, 2, 3, 4, etc. 0 is your background, and then the rest are your classes. So in this case, the data set that they used is Coco data set, so that has 90 classes. And then your metadata can also include other additional things. For example, if you have any normalization configuration that you're doing, because if you're training on normalized images, then at inference time as well, you would have to follow the same procedure. You would also have to normalize your testing images. So any normalization configurations or any other pre-steps that your input image needs to go through before you can predict on it. So all of those, that information would go into your metadata. And once you have that, you can basically embed this into your Android or iOS apps. They have also given this detailed for mobile NX. So they have also given this detailed documentation of how basically once you have the model in the .tf-lite version, how can you basically use it for inference. So you put it in your assets directory. So they've given all of this step-by-step tutorial on how you can do that on your mobile and iOS. Since I'm not an iOS or mobile expert, so this is just, so I'm going to redirect you to these documentations if you want to try this out. So back. So moving back, we're just going to do a little dive into AI consciousness and how basically to understand in a little in depth on how the models basically work on images when we talk about images. So here we can see a simple, some simple neural network pictures, one layer, two layer, and how a neural network looks like. And now this is how a CNN looks like, basically convolutional neural networks looks like. So you have feature learning, and then basically you have the classification segment. How we use these is in object detection. It detects the object and then also gives the accuracy for each of those detections. So this basically what you're looking at right now is the output is what basically the initial layers of the CNN is learning. So the initial layers of the convolutional neural networks look at basically the low level features. What we call the low level features are things like, for example, edges, colors, etc., etc. So these are all the low level features that the initial layers are basically learning. And as we move ahead from one layer to the other, these low level features basically combine up to make objects. So, for example, we can take this analogy of drawing a bicycle, for example. So when you're starting to draw this, you're making these very low level features, for example, just circles, and then you're combining up circles to basically make the tire. Then you're combining up those to basically move forward in how this bicycle looks like, and then there are going to be some completely different shaped parts as well for this cycle, for example, the seat and this handle. And at each of these, basically, as you move forward, you're combining the simple shapes to make more complex shapes, right? So this is exactly how convolutional neural networks also work. So you start off with low level features, for example, edges, colors, etc. And as you move in the layers, you basically the network, how it's learning is that it's combining all of those features to understand what low level features combine up to make the next component, and then the next, and then eventually to create that object. So this is how it would look like for a 5-layer convolutional neural networks that's trained on multiple um, um, classes, from humans to tires to dogs, etc. So if you see the initial layer, you can see that there's a lot of colors and edges and mixture of those things. And as we move to the last layer, things basically begin to form into more ob object related detections. So this is how the layer one, this is what the computer is basically seeing for all of these images. So another interesting technique that helps us to understand the low level and the high level features is basically neural style transfer. So what neural style transfer does is that it takes two images and it takes the style of one image and puts it on, embeds it into the other image. So this is how it would look like after neural style transfer. So it starts off with a very noisy image. And what it does is that it takes two different things from two different images. So it starts to take content from one image and it starts to take style from another image. So in this case, it will start to take, and in each iteration, it's basically taking more of the content one image and more of the style from another image. So if we can think about it in the way that it's taking low level features from one image and it's taking high level features, which are the object level features, from another image. And in each iteration, it continues to do that. And this is how it overall looks like then. So in this case, it's taking the content from the left image. So the content, the object, is basically the line itself, and from the right it's taking the style, so that's being embedded into all the low level features. So it's being embedded into the edges, the colors, all of that is coming. So these are some examples of how it looks like. So looking at this one now, if you notice, it's retaining the high level features from this image, right? So the objects, which is the door, the mosque, the person, so all of this high level feature is coming from this image. And then it's embedding the low level features from this image. So all the low level feature is going into the edges, the colors of that same image. These are some more examples of how this works. And interestingly, Snapchat actually also has this feature. So if you go into your memories, you take one of the pictures, you go to your edit icon, you should be able to see this feature where they have these different images that they give you. And when you click on one of those images, you basically get that style embedded onto your image. So that's where a neural style transfer is actually being applied. So that's about it on my end. If you want to ask any questions, happy to do that answer.
Yeah, I do have a question, but first of all, I'd like to thanks for the presentation. It was great, and maybe let's give a big round of applause for Aqsa for having that presentation. Yeah, it was really insightful and interesting. Yeah, but maybe before my questions, do anyone else have a question? Yeah, either on chat or you can just unmute yourself. You should be able to do it. Okay. If there are no questions, I will start with mine. First of all, I'm wondering what's the pricing model for the TensorFlow, because that's something I'd like to play in Android, but I'm wondering if it's not too pricey.
I'm sorry that. Could you
Yeah.
repeat or could you drop that in the chat? I think that I
Okay.
be, yeah.
So basically, the question is whether the usage of the library is free, or there any.
Yes, yes. It's open source. So
Oh,
there's no cost on it. So you can just use it. Keras is basically the high level API where you don't have to define the code of the layers, or you just have to define import layers and just define your model or use pre-trained models. And as I said, there's also like a model repository from where you can just get the models and try them out. It's open, it's completely open source, so it's free. But if if you're not using for mobile and you're just using for some of your other experimentations, and you want to, their paid services actually come all on Google Cloud. So they have Google Vision, they have Google Text Analytics, they have Google, their conversational chatbot. So all of those services, even though you can use their free trial for some of the things, like for some requests, you can still use it for free. But for scaling and all of those things, they have a limit on how much you can use those APIs in a day. So that's where the cost comes in.
okay.
But with TensorFlow framework, it's completely open source. And Colab, the one that I shared, where I was showing the TF Lite conversions. So that's the notebook that you can also use for training your model. So Colabs is where they also give you GPU access there. So when you're running it in Colab, you're basically running it on their cloud and not on your local machine. So and a lot of the common libraries are already imported in Colab, so you don't have to face a lot of that, installing issues and library downloading issues. So Colab is very good with that. So if you just want to experiment and you want to, even for your developer work, in even in our companies where people are experimenting with different models, they tend to use Colab, for quick experimentations and for faster training.
Great, thanks. And I have another question, whether you heard about DALI 2. Mm, that's something new for me,
Yes.
I guess.
Yeah,
Maybe.
I have heard about it, but I'm yet to experiment on that a little. But yes, I've heard about it. Have you heard about the palm?
No, no, I have not.
That's interesting as well. So that's I think there was this Twitter trend going on with uh the model that can make jokes.
Oh, nice.
So that's an interesting one as well. So that's by Google. the Palm, I think that's the name. So that's the one that was causing the hype around, like it's a chatbot that's making jokes. So that's an interesting thing to see as well.
Do you know maybe, because for now, from what I know, it's closed, like you can register for like to join the tests, but it's not like publicly open yet. I mean the Palm. Do you know of any dates, like when is it coming to be publicly more available?
Hello?
Yeah.
Oh.
Hello.
Okay, I can type in the question.
Yeah, I think I am having a bit of trouble hearing. So if there are any questions, please just drop them in the chat. I'm not sure. Normally what they do is that, sometimes they do open it to requests, like, you can request them, and sometimes they give you access, similar to how, they do it with GPT, and how they've done that previously as well. So some people, but no idea if they're going to, widely open this to public. Sometimes they're just launching some products just to see, what excitement it creates, and then they post develop it into something if it creates more excitement. So I don't know what the real, agenda behind Palm is.
Are there any updates on the allegedly like sentient chatbot? There was some news. I know that like it was probably more clickbait headlines than there was to the real story, but there was one engineer that claimed that there is some intelligent being created at Google. Is there an update on that? Or like, I know that Google said that it's of course not true what this guy claimed. Have you heard about this story? How?
I am having trouble
You
hearing.
still okay?
Unfortunately, I think it's the internet here.
Yeah, Natalia sent
we are facing some load shedding issues here. So I guess it's that.
Yeah, and by the way, I've heard about that story, but I have no idea whether there were any updates on it. Yeah. Okay, so are there any more questions to Aqsa? If not, we can start with Piotr's presentation about Kotlin flows. So I give voice back to you, Piotr.
Okay, good. Let me see if you can see my screen.
Thank you, everyone. And thank you, Natalia and Jacob, for this. Thank you so much.
Okay,
thank you so much.
Okay, I guess Piotr had to reconnect to share the screen. So give him a minute or so.
Hi again. Sorry, I had to restart my Chrome because I had to give some permission to share. Let's see if you can already see everything. Do you see the presentation now?
Yes.
Okay, good. Now I don't see you, but I'll have to manage somehow. So thanks for tuning in. And today's talk is about channels and flows in Kotlin, and titled Hot or Cold, because this is something that I was investigating a little bit recently. So I also thought that I can summarize these two because they sometimes get mixed up. We know that they represent more or less some streams in Kotlin, but here we can maybe go through some more details on it. Generally, channels and flows, as you probably know, are used in the coroutine rules world to solve different problems. They are very versatile, and here, like as a starter, we can see that channels, we can think of them as primitives that are used for basic communication between different coroutines. Flows is an implementation of reactive paradigms in the world of Kotlin coroutines, and as you'll see later, compared to RX, the fact that we can use suspending functions gives us a lot of flexibility, and also simplifies the reactive world that in the times of RX Java could be quite overwhelming. What is the basic problem that channel, let's start with channel, solves is, of course, in asynchronous programming, we can often face the problem of a shared state that different, in this case, coroutines may access and modify, and channel is a solution to this problem, and it allows us to communicate between different coroutines. Here in the code, we can see that we have two different coroutines launched. One sends something to the channel, which may be some heavy computation. The other coroutine receives from this channel. In this primitive example, we can see that, of course, we have to, in this case, know how many items we'll send, how many we will receive, but it's mostly not the case. But general idea is that the channel can receive, and that we can send to channel, and other coroutines can receive from the same channel. What is very important in comparison to flows that we'll see later is that the values can only be received once when we send it to a basic channel. There was something like a broadcast channel that was now replaced by flow. So yeah, as we can see, it's also an evolving, of course, the language is evolving, and we have different solutions to sometimes the same needs, but generally we can remember now that the channel, whatever we send to a channel, it will only be received once on the other end. Here, as you can see on the pictures, we have one sending coroutine that sets some channels, some elements to the channel, and on the other receiving end, we can have multiple coroutines. But we can also have the other situation that multiple coroutines send to a channel, and we can have either one or multiple receivers on the other end. And how it works, the channel is, we can think of it as a first in, first out queue that stores the, like has the coroutines that may receive, and it distributes fairly to the coroutines that call receive. And here we can see the opposite situation where we can have multiple coroutines sending you to a channel, one receiver, and of course we can have multiple coroutines sending to a channel, and also multiple coroutines receiving from it. The important part is that each coroutine will receive only one value. Here we have the same thing in the code. Also added the produce builder function that is usually used to create a channel. Here in this case, we send all elements from a list to the channel, and we have two coroutines that consume on the other end. As you can see here, we can use for loops to consume from a channel, and in this case, we do not need to call receive. And also the produce builder function takes care of closing the channel, which otherwise we would have to do manually. And here's the result. We have two coroutines receiving from a channel in for loops, and each of the coroutines receive some part of the data, which is like fairly distributed between these two. So when the channel is empty and we call receive, it will suspend. So we have also, we can be sure that whatever is sent, the other will not be lost in such a channel. And for channels, we can also define on buffer overflow action. And if we define specific, if we specify a capacity of the channel, which we can also do while creating it, and we reach the channel capacity depending on the buffer overflow action, it will either suspend or drop some of the elements. Yeah, and here, referring to the title of the presentation, important thing to remember is that channels are hot sources of data. So when we create a channel, we, in this case, the compute next value will always execute and not really wait as it would be in case of a cold data source. So here, let's maybe quickly talk about what cold and hot in this context really means. And here I found some analogy that is helpful with a with a remark that I will share later, that a cold data source is like Netflix, so that we can have multiple or many consumers that can call such a data source, and as long as they not subscribe there, the data source does not start to produce, in this case, a stream of a movie. And on the other hand, we can have hot data source, which can be compared to a movie theater, in which the data is produced regardless of the presence of or not of the consumers. Of course, I'm not referring here to the exact implementation, how Netflix implements their streaming service, but just as, about the idea that the consumers connects to a cold data source, and only then the data is really processed and delivered. And on the other hand, hot sources are like always there, and when the subscribers start to observe them, they start to receive the data, but the data is already there and it's not produced on demand. Again, so we can think of cold data sources as more of a description how the data is generated, and as long as they only really start to process it and generate it when there is someone to observe it, and they produce the elements on demand. We can think here of a good analogy is like a description of the source, and not really an action that produces the source, the data. And for cold data sources, each consumer would then get a fresh set generated with the same description. And generally, cold data sources do not store the elements. They produce them on the fly, and because of this, they also have use less memory. So if we have a long sequence of data, when we only produce it on demand, we do not have to store the intermediate results, for example. Here, I mentioned flow and sequence as an example that we'll then go back later to. And on the other hand, hot data sources, they produced independently of the presence of consumers. They store the data. The data is then available immediately. And here on one hand, we have lists, sets, and when talking about here this context, channel in Kotlin. So we have a single producer, we can have a single list, and anyone who reads this list will get this data immediately, but this list will be just there. And as I mentioned already, it's already there. I mentioned the list versus sequence. So here we can have a quick look on that, how it works in both cases. So in case of a sequence, as you can see here, this is purely description of how we want to have this data delivered with some intermediate steps. We have 1 million elements. Each element will be filtered, will be mapped. But as we execute this code, nothing really gets calculated or stored anywhere. And only when we call a so-called terminal operation on such a code source, in this case toList, it then processes each element of the sequence, original sequence, which here is a sequence of 1 million elements, maps it, filters one by one, and only then creates a list. And on the other hand, we can have a list that filters every element and it creates this intermediate result on each step, then maps each element, and then returns the list. So a similar thing to a sequence, then we can have in the world of streams like here channel and flow. Here we are back to the idea that channel is hot, so it would compute the next value immediately. And this is how implementation of flow in Kotlin really started. And so here is a look into the history. Roman Elizarov, which I also will mention at the end, has a great talk on flow and the motivation why flow was implemented, how it was implemented, and some really interesting examples also in comparison to Rx. So I will share the resources at the end. There is a GitHub issue where he specifies that we have channel, but we also would need to have a called stream in Kotlin, because channels in this case do not solve all the requirements or do not fulfill the requirements that we may have. And yeah, that's how flow was born after some time. And here again, compared to the definition of a sequence that I showed earlier, we have a flow builder that is a regular function. This is important, that flows, functions that return flow do not need to be suspend functions. And this is a description how this flow is, which elements this flow will emit once a collection starts. So here we treat it only as a definition of what will happen once it's collected. And about this, what is a flow builder, what operations we can execute on it, and what is a terminal operation. We'll get there in a moment. So what is the difference? Why cannot we actually use a regular sequence builder as mentioned before? And the answer is simple, is that flow gives us additionally the full support of suspending functions. So in a sequence, there is a suspend function yield in this case, which because that's how sequences work, that only when yield is called, then the element is returned or emitted. But they do not support like other suspend functions inside of the builder. The only function that can be called from within this sequence builder is this yield function. And if we wanted to have some asynchronous operation inside of such a sequence builder, this is a operation would be then blocking and not suspending. And yeah, that's where Flow comes in with full support of suspend functions. And it gives us the whole package of advantages of suspending functions, that we have context, and we can handle exceptions, and all the other like structure concurrency that comes with coroutines. So here, collect, we can treat it as like for each of terminal operation for collection, so that this is the final part when we call a flow, where we really need a context to collect. So the flow definition does not need to be executed in a coroutine context. Yeah, and in this case, when we start collecting, that's where this coldness of this source comes in to play, that each collector will then get all the emissions from scratch. And here a summary. So every flow will be defined with a flow builder, some function that creates the flow or defines which elements are emitted. Then we can have a series of operators that modify this flow, or as here in this case of this intermediate operators like on each, on start, on completion, can react to emissions and execute some actions on the elements. So on each will be executed on each. Oh, I think I broke my presentation. Oh, it's there. So on each will be executed on each operation. Are you there? Because I don't hear anything. And
Yeah, we are here, and we can see the presentation once again.
Okay. On completion is after the collection will be finished, and catch, which I want to expand a little bit on more on, is where we can catch the exceptions, whatever exception is thrown upstream from the catch block. So, and here we have the terminal operation on the flow. Going back to catch, as I mentioned, whenever something, some exception is thrown in any of the operations above the catch block, it will be caught here and can be handled, but it will not catch the exceptions that occur below it. So if there is an exception in the collect lambda, it will not be caught by this block here. But there is a simple solution to that. If we want to be sure that all the exceptions are processed, we can simply replace the collect with an on each called before, and then handle exception in the catch block and leave the collect empty. So in this case, we are sure that every exception that occurs in this flow is handled. To some other operators here, if someone, we can all recognize them from regular collections. So each element flowing through the flow can be mapped to another. We can filter the elements. We can merge multiple flows into one. here I want to just comment on the 3 functions that merge flows. Merge, we have 2 flows that then merge into one, and they do not wait for each other, which is important, that like whatever comes first will be then emitted in the resulting flow first. We have zip, which is sometimes confused, but here it works like a zipper in our trousers, for example. So both streams will then be combined into a stream of pairs, and they wait for each other. And the last one we have combine, and in this one every new element forms a new pair. So if we have asynchronous emissions occurring in different times from both flows, then we'll have every new emission paired with emission from the other flow and emitted from the resulting flow here. And all these operators support also suspend functions. And this is where we have an advantage over this complicated RX streams, where we had to have different operators depending on whether or not the operation was asynchronous. So we had flap, map, singles, map, etc. Here we have only map, and we can do whatever we need within the mapping lambda. Question: where such flow will be executed? Here, generally, both in this coroutine context, both emissions and collection happens in the same context, but this can be adjusted. So with flow on operator, we can decide that the elements upstream are executed with a different dispatcher in this case, and what is called context preservation, that whatever like that the context of the collector will be preserved, but the flow can run on a different dispatcher. Okay, here another thing with launch and collect as an operation that is very often executed. There is a shortcut for it. We can, instead of calling scope launch and collect, we can replace it with on each to also do the trick with exception handling that I showed before, and use the shortcut launch in scope. Compared to reactive streams, what we gain using Flow, we have a much simpler API because of the usage of suspend functions, so that we do not need different operators, for example, for asynchronous and synchronous operations. And because of using the usage of suspend function, we also get for free back pressure. So whenever source sends more and faster than the consumer can process, because of this suspension mechanism, we can have back pressure, which means that the elements will then be wait for the collector to process them. If we need to go from one to the other, there is a library that helps us to, with one extension function, transform an RX observable into Flow. So it's also quite convenient. And generally, back to the original question. So are the flows hot or cold? From what I mentioned and how I described it, we can say that they are, of course, cold, because they are this description of how we generate the data, etc. But here is the confusion that sometimes, like when I first started reading about it, I was lost, because on one hand I read, okay, flows are cold, but there are these other flows that are suddenly hot, and it's because basically the builders that I showed are are cold. They are just the description of how the elements are emitted. But there are functions that change how the flow behaves more into the direction of a hot source. So sometimes the resulting flow will be not as cold, or there are implementations that implement the same flow API, but work totally different under the hood. So they on the outside they use the same API, but they are hot sources. So we cannot say that all flows are hot or all flows are cold. The flows created with flow builders are cold, but for example, implementations that are widely used in Android, like shared flow, state flow, channel flow, are hot. So they, going back to the definitions, they will produce data regardless of the presence of the subscribers. Okay, here another example of this flow. Okay, I wanted to first go to the buffers, but I can mention it quickly. We can have another builder channel flow that allows us to combine two coroutines concurrently and send the result into this channel that come from two different coroutines running in parallel. We can also have a callback flow, which is a way to transform a callback API, as here the listener, into a flow. Here you can see why it needed to be introduced. On the top implementation, we have a regular flow which tries to emit a value within the builder. The problem here is that this emit function is it requires to have a coroutine context to run, and with this callback flow we can replace the callback with sending a result to the flow. What is important, we need to call this await clause with optional action that will be executed when the flow is cancelled. I mentioned like transforming a flow which is called into semi-hot flow. There is a function buffer that can introduce a buffer to a flow, so that we can also think of it like a flow that keeps the elements even if they are not collected. And this allows us to also, if let's say this emit was a little bit more complicated and took more time than the collector, the other way around, if the collector takes more time to collect the emissions, but the flow with buffer here can generate them quicker, this buffer allows to for this first generating operation to run in parallel, and then the collector will get the buffered elements. Then we get to shared and state flow, which this is where my initial confusion came from, which are hot flows, and in this sense are very different from the flows defined with the flow builder. They solve the main challenge of like sharing a single source of data for different subscribers. As I mentioned in the beginning, channel had this broadcast channel that was also a hot version of a channel that could have multiple subscribers that would all get the same emissions. Here in shared flow and state flow, we also have the advantage of having a single hot source that can be observed by multiple subscribers. And in the Android world, state flow is very often used to represent the state of a view, for example. So here we have to remember that even if something shares the API with a flow, does not have to behave the same way in this like hot or cold terms. Oh, again, I clicked something wrong. Okay. So stateflow, as I mentioned, is this observable value that we use to represent state, for example, of a view. And again, important note, is a subtype of shared flow. So these are not like one or the other. So stateflow is a shared flow with some limits, with some specific behavior, like that it always has a value available, and it also requires us to initiate with an initial value, but it is also a shared flow in the sense that it has one that the emissions are shared for between all the subscribers. So shared flow is more general. As I said, it doesn't have this initial or always available state value, and it can be customized in some ways that we'll see in a moment. So here is an example of a shared flow. We can have, again, we define the shared flow with a replay value, which I'll explain in a moment. We have some emissions and what this replay value means in this case. Here we can see that we defined the flow got some emissions, but they were not collected. Here again, the hotness. But because of the replay parameter, the newly subscribed collector gets the two last emitted elements, in this case 2 and 3. So the replay parameter, when we define the shared flow, defines how many parameters are kept in a buffer for new subscribers to get. And here we can see that the replay cache is also for a shared flow available to peek, let's say. So if we need to see what the buffer replay cache keeps, we can access it even outside of a coroutine context. And also this cache can be reset. Another point which was very confusing to me originally was this replay and extra buffer capacity. Because as when I initially looked at it, I thought that it may represent the same thing. But generally replay refers to the number of elements that new subscribers will get, and the extra buffer capacity refers to the situation. First, it does not influence the replayed value. So if we say replay 2 and extra buffer for 4, still only 2 elements will be delivered. And the buffer overflow also only is important when there are existing subscribers that cannot collect it. So as long as there are no subscribers, these two values do not mean anything. And what is important, that the buffer, in such case, when we have slow collector, the buffer size is a sum of this replay value and this extra buffer capacity. So here we have a flow that immediately gets 5 elements, and a collector that only receives the last 3 in this case. 3 because it gets 1 replayed emission, and 2 from the extra buffer capacity. Okay. So when we look at shared flow compared to, can you hear me still? Because one of my
Yeah, sure, we can hear you well.
Good. So we have a quick comparison to RxJava. If someone worked with RxJava, we can think of this shared flow as the equivalent or similar to subjects. If we have the replace 0 is a published subject, when we have replace 1 behavior subject, and this behaves similarly to this state flow. And we can also have replay max value, which means that whatever was emitted to this shared flow will be kept for all the new subscribers. Shared flows can be also created from cold flows, again, using this share in function. And it works like this, that it creates under the hood a new flow, and this flow will get all the emissions from the cold flow and share them to within a specified scope. This share in function also accepts replay parameters, so it can be configured in a similar way. Here we have an example of this sharing in action. So here we have two flows, and these two flows are merged. So the resulting flow is still called, but once we call sharing on a specific scope, it creates a new shared flow with a defined policy here. Sharing started lazily, which means that it will not collect the original flow when there are no subscribers. But once there are subscribers, as in this case, they will get the data shared. But here we can see that the first subscriber gets all the emissions, A, B, C, and D, and the other one, since it arrived late to the party and we use the merged operator, only gets the latest one. We go to state flow, another hot flow in Kotlin. So it's similar to shared flow with this replay 0, which means that it always keeps a value, and it can be used as a state container. It requires us to initialize it with a value, so the value is always defined, not like in the shared flow case. And generally, right now, it is the recommended replacement for live data on Android. That's the trend. And it, similarly to the shared flow, has this state in function that can turn a cold flow again, so a flow that was created with this builder, into a state flow that then is shared within a specified scope. It also, since it's this state flow that always requires us to have an initial value, it asks us to provide this initial value. If not, then it will suspend until this value is set. Before I wrap up, I want to share a short demo of a problem that I had recently, which also involves using flows.
Okay. Here we have a simple app. Okay. So what was the problem? The problem was that we had multiple coroutines updating some state over the network. That here we can see this in action. Each click on this element starts a request that updates some state, and this state is then received. And the problem we had was that when these calls were executed in parallel, and this was a long-running operation, sometimes the state that appeared first was not the one that we were really interested in right now, because it was already updated by the second operation that was started. So when we executed it slowly, then each update came back and updated the UI correctly. But we sometimes got weird state that represented, like, we wanted to send 3 updates, but because of a race condition that the first request returned us a wrong value that did not take into consideration what we did later, we ended up in a weird state like this. Yeah, and what we did here, and what also shows that a flow can be used, or a channel can be used to force a sequential operation or sequential execution of launched coroutines. I can show you a little bit the code. So here is a fake repository that for each of these tasks, when we update it, simulates a long-running answer, which returns us some wrong state. And to force it to run in sequence, we can create a flow. Here is the example where we, again, when I clicked on this task in this buggy example, I just executed, yeah, here is the, let's say I just executed some request, fire and forget, but since we were observing the state on other layers, it would leave us in a invalid state then. And how it could be fixed, and how we can enforce in such case a sequential execution of few jobs, so that every job waits for the other to finish, is also using a flow in this case. This is a little bit, let's go through it step by step. So here we create a job instead of running the task and forgetting about it. Let's say we create a job, we emit it to the flow then joins them so that they only then get executed. And with this like neat trick workaround, we can ensure that the whatever is executed in a sequence here will also keep this sequence here, as I have in another fragment that fixes this problem. So we call these 3 operations. They get skewed in this flow, and thanks to flow supporting suspending functions, we can control this sequential execution like this. The most important parameter that allows us to do this is here, this launch with lazy, which means that this coroutine, even though it's launched, it will not be launched eagerly. It will not be launched immediately. This job will be only launched when we call join on it, and this join is executed on on each element of this this flow. Okay, do I have anything else? Yeah, I have one very important part, the resources. Totally recommendable. The book by Marcin Moskała. I read it recently. It's a really well structured, with great examples, explanation of coroutines, and also, among other topics, channels and flows. He goes into, in my opinion, the exactly needed amount of details, because I realized that there were some points where I thought that this is an implementation detail that I'm not really interested in, and only after reading the explanation I thought that I realized that it gives you only then, once you understand what's happening under the hood, you can better understand the bigger picture. So totally recommendable. Marcin Moskała, Kotlin Coroutines. He also is an author of Effective Kotlin. So read it and support the author. Of course, Roman Elizarov that I mentioned, he's the lead developer on Kotlin language, and he also has a great presentation about synchronous data streams in Kotlin. Good. Do you have any questions?
I do have a question about channels, and I'm wondering if both shared flows and channels are hot flow, are there any use cases where I'd like to use channels instead of shared flows?
Yes, there are differences. There are differences. First, if you want to make sure that for example, if we have a hot flow that is not observed, here it depends a little bit on the configuration, because playing with the parameters like buffers, etc., you can, and the buffer overflow, you can tweak this this behavior. But generally, I would say that if you want to make sure that for example, all the events, if you keep the events in a channel, you have the guarantee that as long as you have one observer, that all the events will be delivered. And if you have this shared flow of events, for example, you may lost some of the events if they are not being observed. So here, I think it depends a little bit on the case and the requirements. And channels, I think you can use them well in some scenarios, like when you have multiple coroutines that the scenario where you have multiple coroutines, and wait a second, I'm looking for the, I think I went through an example like this. I think, like, conceptually, it's in most of the cases you could use flow or the shared flow here, but if you want to have I think a little bit lightweight implementation, and you really know exactly what you want to do on this, like inter coroutine communication, then you can handle it probably better with channels. But I cannot find right now the good example that I went through.
Yeah, thanks. No problem. Yeah, it was great presentation. Thanks a lot for it. Yeah, again, a round of applause for the presentation. And yeah, I really like the part of explaining differences between hot and cold flows, because the example was really visible, and hot and cold flows are things that always confuses me.
Yeah, this is how this all was born, because we had these discussions also at our work, and we realized that we know more or less, but since the documentation mentions them here and there, in the same more or less context, because everything mentions flows, everything mentions shared flows. We assume them, okay, they should be the same thing, but they differ very much depending on which operator you use. If it's a channel flow, it behaves differently than if you build it with a flow. So one thing to remember, that you have to really see how it behaves. And the same thing was with the shared flow, that the parameters that you define on buffer flow, overflow action, and the buffer size and the extra capacity can change significantly what you receive on the collector, because it can change from a flow that drops everything when there are no subscribers, to a flow that keeps everything and delivers the whole history using this replay parameter, for example. So it's important to see what are the defaults, understand how it behaves with these three parameters that I showed you, and then remember that optimally on the receiving side, it should not make a difference for us which type of flow we use, because it's also a pattern that we expose everything as a flow on the receiving side, and only on the layer that is responsible for publishing to the flow, we are aware what are the internal workings of the flow, but the collectors usually should not care what's happening under the hood. I think I have one more slide that is also quite important now, if for anyone working with Android, because if you go through some tutorials that are just a little bit outdated, you can see, for example, flows that are being launched with life cycle scope on started. And recently, the new proper way here, it's also wrapped in an extension function on flow. But if you plan to replace live data with state flow, you should use this repeat on lifecycle, because what it gives us is that, for example, when the app goes to the background, it not only stops processing the collection, but also stops if we are observing a hot flow, it will stop the hot flow from generating the data, because it cancels the whole flow when we go, in this case, from started to destroyed. So check all the latest stuff, because I don't know, it was some article a few months ago. So to be always up to date and use the most recommended way of doing things.
Yeah, or at least be aware of it.
Yeah, or at least be aware, because this is something that we not always think about, that even after we go to the background, there may be some active flow, for example, using our resources, or using resources most. That's the problem that we face here. Good.
Even if coroutines may look simple at the first sight, their internals are quite complicated, and there are a lot of traps that we need to be aware of.
Yes. With cancellation, for example, it's a very different story that I thought it is before reading this book, for example. So definitely, I recommend going through it, because for me, it was a game changer. Good. So thanks for your attention, and I hope you enjoyed it.
So thanks once again for the presentation, and yeah, I guess we have still some time to discuss other topics if anyone have question related to Android or coroutines or anything like that.
I'm just going for my charger.
Yeah. Okay. So if there are no topics that you'd like to discuss or ask or anything like that, I just like to invite you to our social medias that Natalia put into the Slack, into the chat. I invite you especially into Slack. where there are all informations about our other meetings. The next meeting is planned to the second half of the October. So yeah, follow the social media to know where exactly and when will the meeting be. This meeting will be offline, so we can have another possibility to meet and talk in offline environment. Yeah, I guess that's everything for today. Presentations were really interesting and really insightful. So yeah, I hope you learned a lot in today's meeting. Yeah.
Thanks, Kuba, for organizing, and thanks, Natalia. I don't know, Natalia, you're still here, but
Yes, I'm still here.
yeah, thanks for organizing.
Thank you so much.
It's the first time that I did something like this, like online presentation. It's fun. And
it went really well.
Yeah, I don't believe it was the first time, because the presentation was
Exactly.
very well prepared and really good. So yeah,
Thanks a lot.
must be lying on that. Yeah. So yeah, I think we can end the meeting now.
Thank you so much, everybody, and
see you next time.
see you next time. Bye bye.
Yeah, bye.